Great. Thank you so much for inviting me to speak today. So this is the Markov equation. It's cubic in 3 variables. And we're going to be interested in the integer solutions modulo a prime. So there's the trivial solution. And if you do some math, then you can come up with another solution, 3 through 3. That one's going to work for all primes. Well, primes greater than 3. Actually, if you start from 3 through 3, you can come up with all of the other solutions. Well, over the integers, you can come up with all of the other solutions via these 3 so-called Vieta involutions, where you take one of your coordinates and you swap it out. This is equivalent to fixing 2 of your variables and then solving the quadratic in the remaining variable, and then flipping over to the other root. So we have a conjecture that for all primes p, these 3 involutions will actually generate all of the solutions for the Markov equation, starting from 3 through 3. So for the integers, this is the Markov tree. It's infinite 3 regular tree. And for the integers, we already know that this contains all of the solutions. If you take modulo p, then you get a quotient of that tree that gives you the Markov graph modulo p. And the question is, are all of the solutions modulo p here? Or are there solutions modulo p that don't lift back to the integers? So that's the question. So the current progress on deciding the connectivity of this graph modulo p, De Courcy, Ireland, and Lee, they were studying spectral properties of these graphs, and along the way, they computed the graph up to 3,000 that it was connected. We have some partial results from my advisor, Elena Fuchs. They came up with a test that, based on the factorization of p plus and minus 1, it's able to show that a lot of these values are, the graph is connected, but not all of them. It's inconclusive for some of them. Although you eventually hit a certain point after which they are all connected. Yeah, there's the number line here is not to scale. My project has been looking at this problem computationally, and my contribution is that I was able to compute that this is connected all the way through 1 million, along with some random samplings through about 50 million, but exhaustive search through 1 million. So how does it work? Bourgain, Gambard, and Sarnak, they looked at the rotation map, which is a Vieta involution plus a swap on 2 coordinates. It fixes one of the coordinates. And then if you do some more math, what you end up with is, based on this value of A, you get that these trace out conic sections. And you get hyperbolas of order dividing p minus 1. You get ellipses of order dividing p plus 1. And then some parabolas that have order exactly p or 2p. So just to give this a visual depiction, you start from some point ABC. You apply the rotation map, and every point on this conic section is going to have the same fixed value A. And along the way, you can switch over to fixing a different coordinate. And so here on this conic section, every point has the same fixed second value, and they intersect here. And so you're going to get lots of these conic sections that all intersect. Some of them are going to be bigger than others, but some of them are going to be of the largest possible order, which is p plus or minus 1. And the maximal order conic sections, those are all connected. And Bourgain, Gambard, and Sarnak were able to show that if your conic section is big enough, then it's also connected to all of those maximal order sections. And so the game now is checking all of the conic sections that are not so big. And we wonder whether those things could actually all just be connected together. So there's some my contribution computationally was that there's a fairly nice way to cook up representatives of these smaller conics. And when you are able to do that, you're able to check whether these graphs are connected in almost linear time. And so here's a graph of checking prime p versus the runtime in milliseconds. for my implementation of this algorithm. And yeah, almost linear. So it's runtime OP to the 1 plus epsilon for all epsilon greater than 0. Yeah, so future work, we would like to be able to run this on larger primes. We would like to bound the diameter of this graph. And it would be nice to generalize to other Markov equations, not just the 0 set of that original equation, but setting it to arbitrary k. All right, yeah, thank you very much.